We are in Unit 10, and this is day 2 of Notes 3. So we are continuing with our area of polar graphs, and in this, we're just going to dive right in, continue where we left off on day 1. So this is example 10. The graphs of r is equal to 2 minus sine theta and r is equal to 3 sine theta are shown on the right. Find the area, this is a typo here, it should say of the shaded area, okay? So I can graph these on Desmos and print them off really nicely, but I don't know how to shade, so that was shaded by hand. Alright, so let's see. It would be nice to know which is which. So which is which? Which is the top one? Well, the top one would be the positive sign one, right? The bottom one down on the lower y-axis would be the negative sign one. This is a circle. This is a Lima song with no loop. Okay? Don't have to know that, but it's helpful. All right? So, when you're given two graphs and you're asked to find something with the area where the area that you want to find is in any way related to both graphs, you have to find the theta intersection values. So here is the point, I mean they intersect all along here, right? But the point where I'm looking is right here. I want to find that theta value. And I want to find that theta value. Okay? It looks like it might be pi over 6. That's visually what it looks like, but we have to make sure, right? We need to find out. So we need to find these two theta values. There is definitely symmetry going on, right? So let's go ahead and find these two theta values. So to find out where the two curves intersect, we set r's equal to each other. So we're going to set these equal and solve for theta. So I'm going to add sine theta to the other side and then divide both sides by 4, and we're going to get sine theta is 1/2. Well, what theta values make sine a half? Pi over 6 and 5 pi over 6, right? So our guesstimate was correct. That is pi over, this one is pi over 6. And this one is 5 pi over 6. Okay? All right. Well, that's helpful. Now, right now, if we found the integral of, so I want the area of the circle, but only between pi over 6 and 5 pi over 6. Pi over 6, 5 pi over 6, in just the circle. So 1/2 r squared d theta. What would that give me? That would give me, so here's just the graph of the circle. Okay? So that would give me, let me switch colors here, that green is a little light. That would give me, I would start at pi over 6, so I'm starting at pi over 6, and I'd be finding all of these sectors all the way to 5 pi over 6. So I can get all those in. All the way to 5 pi over 6. Okay? So I would not be getting these two little pieces down here. Okay? So I would only be getting in between pi over 6 and 5 pi over 6. It is important to know, you guys, that we're starting at pi over 6 and we're going to 5 pi over 6. Okay? If we wrote the integral from 5 pi over 6 to like 13 pi over 6, we would get these two little pieces. All right? Okay. So is that what we want? No, it's not what we want, because we don't want that Lima song. We don't want this shaded piece there. So we need to subtract out the same pi over 6 to 5 pi over 6 of the Lima song. Okay? So we're subtracting pi over 6 to 5 pi over 6 of 1/2 of that r squared. Now, since we have the same boundaries, we could combine these and make it the same integral. You can only do that if your boundaries are the same, but I could have written that like this. Kind of looks like our pi big R squared minus our pi little r squared, and that is very, very similar to what we're doing here. Okay. Now this 1/2 could come out, right? It could come out. So if we were asked to find the integral that gives the area, then they might write it in this form with the 1/2 outside. Okay. When we put this into our calculator, we will do it very carefully because it's a little bit involved, right? So this would come out to be 5.196. That's it. So find your theta intersection values, and then think. Look at what you have. Think, right? Don't try to memorize, oh, it's always this one minus this one, it's always these. Think about what we're doing there. Okay? We're going from pi over 6 to 5 pi over 6. So clearly we need to subtract out this piece. Okay. Let's take a look at number 11. The graphs of 4 minus 3 cosine theta r equals, and r equals 3 plus 2 cosine theta are shown on the right. Find the common interior area. Common interior area. So clearly the common interior area is going to be this odd-shaped piece right here, right? So it involves both graphs. So we are going to begin again by finding the intersection theta values. I like to draw them in because it helps me visualize where my area will be when I make an integral. So I like to draw these in. Okay. Again, clearly there's some symmetry in there. I'm going to find this theta value, and then I'm going to use symmetry to get this theta value, depending on how I want it written. And you'll see what I mean by that in just a second. Not sure how I feel about that little lime green pen. Okay, so common, the intersection theta values. So set the two r's equal, and then solve for theta. Okay. Sometimes you might need a calculator to solve for theta, and if you do, that's fine. You'll just get a decimal, and that's okay. Instead of pi's, you'll get a decimal. Not a problem. So we're going to add 3 cosine theta, so I'll have 5 cosine theta, and then I'm going to subtract the 3, and I get a 1. This is one of the ones where we need a calculator. So cosine theta is 1/5. Okay? So this was one where I need a calculator to find that theta intersection point. Okay? So you can do that a couple of different ways, right? You can do it with arc. In this case, since I really only want this one, I think I'm just going to use arc cosine, because it'll just give me that first positive value. So I'm just going to do that this time. You could also set the two graphs equal and find out where they intersect using function mode. Stay in function mode. Alright? But in this case, I'm just going to do arc cosine because it's the quickest. So I get theta is equal to 1.369438 ... Remember, for AP, all you have to write is 3 decimal places. But your answer has to be accurate to 3 decimal places. This is not our final answer. So we want to use this whole thing, right? So I don't want to have to keep going back to it, so I'm going to call that A. So I'm going to store that in for A, and now it's there. Okay, and I'm going to tell AP I'm going to do that. I'm going to say let's let that equal A, and then I don't have to keep writing this decimal either. Okay? All right, back to our graph. We're going to think about this, right? Okay, I'm going to pick one of the, I think I'm going to start with this area right here. I'm going to start with this area right here. So, for this area right here, I can only go counterclockwise. So you cannot start here and go clockwise. Can't do it. The integral has to start with the lower one and go to the bigger one. Okay? So we have to start down here. And we have to go up here. Okay? So what do I want to name this? So I'm going to have an integral. I'm going to keep it orange for that one. Okay? The orange integral will represent this orange area here. So I know what the inside's going to be. That's not the hard part. Which graph is this? I'm going to that graph. So which graph is that? This graph is a part of the big one, right? The big one with the negative cosine. So it's this one. So think about which graph you're going to. So I need to use the 4 minus 3 cosine theta. That's the easy part. Knowing which graph it goes to, that's the easy part. The hard part is always the boundaries. So I want to start here, and I want to end here. So I'm ending at A, right? I'm ending at A. So I know A is up there. What can I name this? In this case, I need to start at negative A. So I need to start at negative A and go to positive A. Perfect. So that gives me the area of the orange region. Now let's take a look at the other part of this region. So we got the orange part. Now let's take a look. I think I'm going to do this one, get something to contrast. Let's try this little baby blue one. All right, so now we're going to go find this area. So keep in mind that you can only go counterclockwise. So we cannot start here and go clockwise. We have to start up here and go this way. It's the only way we can go. So I need to start at A. So I'm going to start at A. Okay, and then we're going to go and grab all of this area. So I'm starting at A, and I'm going to end down here. Okay, so I'm starting at A. I know what my inside's going to be. This curve is the positive cosine curve. So 1/2 of that curve squared d theta. Now where do I end? I'm starting at A. I'm ending. I can see where I end, but what do I want to name it? Not negative A, because then I would be going from A to a negative A. And that's not where I want to go. I want to go this way. So what do I call that? What do I call that? Well, I can think of a couple things that we could do here. One thing that we could do is call this is 2 pi minus A, right? That would make it a positive angle. So we could say 2 pi minus A, that would work. That would be fine. The other thing that we could do here is we could go from A just to pi and then double it. because are these two not the same? So if you don't like thinking of the 2 pi minus a, then we could change that to double a to pi. Same 1/2 pi r squared. I'm sorry, no pi. 1/2 r squared d theta. Okay? Then we're going to take these two and we're going to add them together. And when you add those together, we get 12.784. So a lot of what we do in calculus is very conceptual. This, it definitely is a little conceptual, but it's so visual as well. I find some students really enjoy this unit because it's very visual with the polars. Okay? It's also a little challenging. It makes you think a little bit. But I love finding these areas of different things. I love thinking about, okay, what do I need to do to get that area? Okay? Because remember, you can call these theta values an infinite number of things. I could call this a. I could call it 2 pi plus a if I wanted to. I could call it 4 pi plus a. Okay? I could call it 2 pi minus a. Anyway, there's lots of different things I could call it. So keep that in mind. All right, next up, example 12. So in example 12, we hit a full-blown FRQ, like an AP style FRQ. Okay, so let's just see what they ask, because they can ask a lot. All right. A curve is drawn in the xy plane and is described by the polar equation r is equal to 2 plus sine of 2 theta. This is not one of our known curves. They did it for us. This, by the way, would be with a calculator. This is with a calculator, all right? Which means we could, if we wanted to, go to polar mode on our calculator and graph it. Right? We could, but in general, I find I don't have to on these. And I want to stay in function mode. Remember, and you can write this on your notes, function mode for all computations. Okay? That is kind of a I know that there are some computations that you could do in polar mode as well, but since you can do all of them in function mode, why not just leave it in function mode? All right? There's really no reason to go to polar mode for these, unless you just can't stand it and you want to see what else is going on with this graph. All right. So it says that it's graphed for pi over 2 to 3 pi over 2. Let's think about that. Pi over 2 to 3 pi over 2. Does that not make sense? That makes a ton of sense. Okay? Pi over 2 to 3 pi over 2. This tells me, and really, sine can at most be, at the minimum, it's a -1, and at the most, it's 1. So r here is always positive. So these are the nice ones. When r is always positive, that's pretty sweet. Okay, find the area bounded by the curve and the y-axis. The area bounded by the curve and the y-axis. Okay, well that's a straightforward pi to 3 pi over 2. Sorry, pi to 3 pi over 2. And then we just know 1/2 r squared d theta. So this area will be 1/2 r squared. Since there's only one r in this problem, I could just write r squared, okay? And we are going from pi over 2 to 3 pi over 2. Okay, carefully put that in your calculator, and we get 7.069, rounded to 3 decimal places. Okay? Find the angle theta that corresponds to the point or points on the curve with x coordinate -2. See, this is one that it just seems like it comes out of left field. Okay? Let's think about this. This is a thinking question. AP is going to make you think. There's no way I could give you every example of what AP could ask. Okay? All right. We want the x coordinate to be -2. Well, where is that? Here's x is -2. Wait a second. Here's x is -2. Gosh, it looks like theta is pi there, doesn't it? And it looks like there's another one where x is -2. I'm visualizing this x is -2 line. And there are definitely 2 points. And I want to find both of those points, right? So, how do we do that? Well, we know that x is -2. We know x is -2. We also know an equation for x in polars. We know that x is equal to r cosine theta. And we know what r is. So we know x is equal to 2 plus sine of 2 theta times cosine theta. And now we want that to be -2. Definitely a thinking question. If they're asking you something about x or y, you're going to be using these. Okay? So now, calculator time. I'm going to go into my equation mode, and I'm going to put this in where I'm at my x is going to be the theta here. Okay, so carefully type it in. Okay, and I'm setting it equal to -2, so I think this time I'm going to put -2 over here. So we're just going to find the intersection. And I know that it's going to be between pi over 2 and 3 pi over 2. You guys, please restrict your windows. Please take the moment to go to your window and restrict that. Otherwise, you're going to see way more than you want to, and it will confuse you. And you'll be saying, wait a second, which one is this, and where is it? And I've seen it before. Okay? So for my y's, I just need to be sure I include -2, right? This includes -2, but just barely. I think I'm going to go like to -5. That's fine, whatever. Really, it just needs to include -2. So here's this weird curve here. And there's -2. So I just need to find where they intersect. Second calc 5, enter, enter, enter. And sure enough, that's pi. So visually it looked like pi, and it is pi. So I'm going to say at theta is equal to, and I'm just going to round it to 3 decimal places. Okay, but if you put pi there, that's fine, because your answer will be correct to 3 decimal places. Okay? Now let's get this other theta value. Second calc 5. Get over here a little bit closer. Enter, enter, enter. And there's our second theta intersection value, 3.981. Okay? So did we answer the question? Find the angle theta that corresponds to the points on the curve with x coordinate -2. Yes. Okay. So pi and 3.981. Okay. All right. Find the angle theta that corresponds to the points on the curve with y coordinate -1. Y coordinate -1. So y -1 it looks to me like there's just one value of theta. So we're going to be looking for this value of theta, where y is -1. So y is equal to r sine theta. So r is 2 plus sine of 2 theta. And this time we're going to multiply that by sine theta because we know something about, or we want something about y. We want y to be -1. So let's find these theta values. So I'm going to come back to my equation. My first r, my r part is fine. I just need to change cosine to sine. And then I need to change this to a -1. And I think I'm just going to keep my window exactly the same because this still includes -1. Should just be one intersection value, and there is. Second calc 5, enter, enter, enter. And that theta is 3.522. Okay? All right, not bad, but you have to think. Usually they start off with a nice sweet little area. That's the mulligan. That's the one that you get, that you for sure will get. And then you're going to have to think. Okay? Make sure you show your work. No bald answers. A bald answer is where you put a number and you have no idea where it came. We have no idea where it came from. Okay? Number 13. So this was from 2014, and this was number 2 with the calculator. And I'm looking at it, I think that this was the entire, it went through D. This is the entire question. So this is fantastic. This will give you an idea of what the AP exam is like when they're asking about polar. Okay? The graphs of the polar curves r equals 3. That's just a circle centered at the origin of radius 3, right? So that will be this one. Circle centered at the origin, radius 3. Okay? And r is equal to 3 minus 2 sine of 2 theta. Well, that's a weird one. That's one that we don't know a name of that graph, right? It's this other kind of fun and funky graph like that, are shown in the figure for 0 to pi. 0 to pi. Does it make sense that these would be 0 to pi? Absolutely, because look at, here's theta equals 0, and all the action is going between 0 and pi. So here again, and I'm looking to confirm, here again, all r is positive all over the place. Okay? Part A. Let r be the shaded region that is inside the graph of r equals 3 and inside the graph of r equals 3 minus 2 sine of 2 theta. Find the area of r. They do this a lot, you guys. They will shade and they will describe what's happening. Okay? So we essentially just need to find the area of that shaded region. So let's think about this. For this piece, I mean, to me it's pretty obvious that for this section I'm going to the weird curve. So between 0 and pi over 2 I'm going to the weird curve, and between pi over 2 and pi I'm going to that circle. Do you agree? Do you want to confirm that this is pi over 2 first? That might not be a bad idea, I guess. Yeah? Let's confirm that that actually is pi over 2, and it doesn't just look like pi over 2. So if we take these two, and set them equal to each other, and in my window I'm going to go between 0 and pi. Okay, and what's the most this could be? The most this could be is 5, right? So I think I'm going to just go, I think I'm going to go from like -2 to 6. So there's r equals 3. Let's find this intersection value here. And it is pi over 2. Oh, can't see that. That is pi over 2. We recognize that decimal is pi over 2. Okay, so we're just going to do this piece by piece. The first integral just goes to this weird curve, so the integrand will be 1/2 of that odd curve, 3 minus 2 sine of 2 theta squared d theta. And for the boundaries, I'm going from 0 to pi over 2. And I'm going to add the next area. Well, the next area, I could set up an integral for it, but it is 1/4 of a circle of radius 3. So I think I'm just going to do 1/4 pi times 3 squared. But if you want to set up an integral, that's fine. You will get full credit. So when we set this, when you stick this all into your calculator, I'm going to save a moment of time and just tell you what the answer is, but you should get this. So, but do put that in and make sure you can get that. Okay? All right, part B. For the curve 3, so for the interesting curve. For the interesting curve, find the value of dx d theta at theta equals pi over 6. Dx d theta at theta equals pi over 6. If they're asking me something about x, what are we going to need to use? X is equal to r cosine theta. R cosine theta, right? We need dx d theta at theta equals pi over 6, and they were kind enough to give me a calculator to use. So if you want to write that derivative out by hand and then plug in pi over 6, go for it. But there's a derivative function on our calculator that is handy, okay? And it will save us some time. It'll save us even more time if I stop talking. Okay, so I do have that function already in for y2, but I think I'm just gonna type it all in again. So math 8, that's the derivative button, and I'm going to call theta x here just because it's easier, it's a little quicker to grab. So I have parentheses 3 minus 2 sine 2 theta, close the parentheses on the 2x, close the parentheses on the 3 on the r, and then multiply by cosine theta, close the parentheses on the x, the last parentheses is automatic, and then we want to evaluate this at pi over 6. So we get negative 2.366. And clearly, if you did this by hand, you would get some square roots of 3's in there and stuff, and that's fine. But we didn't have to, and then we saved time. And time is golden for the AP exam because you're for sure not going to finish it. So if you can save a little time, save a little time. All right. The distance between the two curves changes for 0 to pi over 2. Okay, before I go further, let me see what they're talking about. So first of all, only between 0 and pi over 2, they tell me that the distance between the two curves changes. Okay, you know how when we did function mode, we always did like top minus bottom or right minus left? If I'm talking about distance between curves in polars, I'm not going to do top minus bottom, and I'm not going to do right minus left. I'm going to do outer minus inner along a line that would go through the origin, all right? So think outer minus inner along a line that goes through the pole. So here, that's that distance. If I did this line, it would be this distance. If I did this line, yeah, that distance is bigger, isn't it? And then this distance looks like it's the biggest, and then looks like the distance shrinks a little bit as it goes here. And then it keeps shrinking until, at this point, the distance is 0. At this point, the distance is 0. The distance between the two curves, okay? So yeah, the distance between the two curves is changing. I agree. Find the rate at which the distance between the two curves is changing with respect to theta when theta is pi over 3. So we want the rate that the distance is changing. So I think I need an equation for distance. What is the equation for the distance between these two curves? I'm going to call it capital D for distance. You can call it something else if you like. Okay. The distance between the two curves, think outer minus inner. Outer minus inner. So this is r equals 3, and this is r equals the other equation. So the distance will be 3 minus that other equation. That's that distance. I can definitely clean it up, and it might help me type into my calculator a little bit better. I'm going to clean this guy up. 3 minus 3 is 0, and negative distributed to that sign will be a 2 sine of 2 theta. Now so I have the distance. I have my distance. Now I need the rate the distance is changing at pi over 3. So I need the derivative of the distance with respect to theta. It says with respect to theta at theta equals pi over 3. And we have a calculator that does derivatives at a point. Math 8 for derivative. I'm going to let x be theta again. And I just have 2 sine of 2 theta, close on the argument, and then at pi over 3. So you can put negative 1.999, but this rounds to negative 2, and I know if we did this by hand, we would get negative 2. Okay? So I'm going to put negative 2. All right, very good. Now, what do they say? A particle is now moving along the weird curve. So now we've got a particle moving. Perfect. I love these. A particle is now moving along this curve so that d theta dt is equal to 3 for all times greater than 0. Find the value of dr dt when theta is pi over 6. Great thinking problem. Got a particle moving. d theta dt is 3. Find dr dt at theta equals pi over 6. You guys, this is related rates. Way back from Unit 2, we did related rates. So it's a particle motion problem, and it's a related rates problem, and it's a polar question all in one. It's like they struck gold. Okay? So I know that r is equal to 3 minus 2 sine of 2 theta. I know that's true. If I want to get dt involved, what am I going to do on both sides? If I want dt involved, I just take the derivative of both sides with respect to t. So derivative of both sides with respect to t. That's all related rates is. Kids get so scared of related rates. I think back in Unit 2 it seemed scary. But at this point, you guys, that's all related rates is. You just take the derivative of both sides with whatever you want it to be. In this case, dt. All related rates is. So over here we have dr dt. And over here we have the derivative with respect to t, so it is implicit. The derivative of 3 is 0. The derivative of negative 2 sine of 2 theta, it will still be negative because the derivative of sine is positive cosine. So it stays at negative, and then we're going to need a 4 cosine of 2 theta, right? D theta dt, because we're taking the derivative with respect to t. So just a little implicit differentiation. After you take the derivative, plug in your numbers. That's all there is to it. So at theta equals pi over 6, dr dt, it will equal negative 4 cosine 2 times pi over 6 times 3. And this is a safe stop spot, you guys. That's safe stop. If you want to, you can put that in your calculator, though, and get negative 6. Or you can do it by hand pretty easily, because 2 times pi over 6 is pi over 3. Cosine of pi over 3 is a half. Half of 4 is 2. Negative 2 times 3 is negative 6. Okay? When you're doing these problems, your mind is going to be pretty much fried when you're doing one of these FRQs. You will have already spent, you would have already done all of the multiple choice, and you're starting, this was number 2 on the FRQs, and your brain's going to be a little bit fried. So you may want to say stop when you can, alright? There's a lot of times when kids risk it. They think, oh, I know what cosine of pi over 3 is. And they take an unnecessary risk. When your brain is tired, you can do goofy things. I do goofy things even when my brain isn't tired. So it's a good idea to safe stop for me anyway. All right. I think that's all of our examples. Let me make sure. Yes, that's all of our examples. So we're done with Unit 10 with the notes for Unit 10. So time for you to go and try some on your own and think about these guys. They're so fun to do. I hope you enjoy them. I'm thinking you will.